So we move on to ASA Congruence here in section 4.5. I don't think I should have to say much in way of introduction of this. This will be another triangle congruence shortcut, and you can probably guess what it says just based upon its name. That is ASA. So here we go. It says this. If two angles and the included side of one triangle equal two angles in the included side of a second triangle, then those triangles are congruent. So let's take a look at a picture of this just to make sure that we understand. Of course, pictorially, it's much easier to understand than when it's written out. So I have two triangles ABC and RST. And notice that I do have two angles of one equal to two angles of the other. So angle A is equal to angle R, so that's one of the A's. And angle C is equal to angle T, that's another one of the A's. And then the included sides are equal, okay? That is, AC and RT are equal in length. And notice that to say they're included means they're in between the equal angles, right? So it wouldn't be good enough, or it wouldn't be right to say, well, if we also knew that AB, segment AB was equal to segment ST, then the triangles would be congruent because those sides are not in between the congruent angles, okay? So notice that the order of the letters in ASA tells you what the structure of equalities must be in the diagram. Okay, so the equal sides must be in between the equal angles. But if we have the proper structure here, if we have the proper equalities, we can then say that triangle ABC is congruent to triangle RST. And now, of course, we have to discuss the proof of this. This is a theorem like SSS. It is not a postulate as was SAS congruence. So let us talk about how we will prove this. Sorry about that. So we've got a given, of course, right? So the given tells us that we have two pairs of equal angles and a pair of included equal sides. So AC equals RT, that's the included equal sides. And likewise, the measure of angle A is equal to the measure of angle R. The measure of angle C is equal to the measure of angle T. And we wish to prove that the triangles are congruent. Okay. Now, as for how this will be done, we will follow Euclid on this. And Euclid's proof is absolutely ingenious. It is indirect, and we're familiar with indirect proof. We've given indirect proofs here. We know how those go, right? But it's indirect. The strategy in this indirect proof is a bit different than the strategies that we have seen before. We will not assume that the triangles are not congruent. Okay, that's not the assumption that we will make. Let's go back and look at the proof setup. That's probably what you would expect, because in all the indirect proof that we did previously, we would assume the negation of what we wish to prove. Instead, in this case, instead of that, in this case, we will assume that a second pair of sides that would have to correspond are not equal in length. Okay, so we might, for instance, assume that AB is not equal to RS. And let's talk for a moment about. I'll just stay on this slide. Let's talk for a moment about how this will work out. Okay, so we will assume that AB is not equal to RS. We will prove that this leads to a contradiction, that assumption, and then we will conclude that, of course, since the statement that entails a contradiction cannot be true, it will follow that AB does equal RS. And once that AB does equal RS, once we know that, we will be able to say by SAS congruence that the triangles are congruent. Okay, the triangles are congruent. So that's the basic strategy here. So what we will assume is this: we will assume that AB is not equal to RS. Now, by the law of trichotomy, it follows that AB is either greater than RS or AB is less than RS. We'll only consider the possibility that AB is greater than RS. If AB were less than RS, the proof would be exactly similar. So this is that kind of move that I've allowed you to make in the past. That is, if you've already done the work, really, and what you would have to do to complete the proof is exactly similar in structure to the proof that you've given already, then there's no need to do it. That's just needless repetition. Okay, so we'll only consider the possibility that AB is RS, and we'll note that if AB is less than RS, the proof will work out in exactly the same way. Okay, so we've assumed that AB is not equal to RS, and that in particular AB is greater than RS. Now, here's something that this will mean, and I'll show you a picture to illustrate in just a moment. This means that there will exist a point Z on AB such that AZ is equal to RS. Now, why would that be the case? Well, AB is greater than RS, right? That is, AB is RS plus more. That's what greater than means, of course. It is RS plus more. So let us mark AZ so that, let us place the point AZ so that AZ is equal to RS. And then the more would be that piece CB. And this is absolutely allowed by our constructions handout. It is one of our construction rules. It is construction rule C2. So here's what this looks like. Okay, so we said that AB was greater than RS, so we may construct a point Z on AB so that AZ is equal to RS. So there it is. Okay, AB is greater, so I can pick out a part that is equal, and the part that is equal to RS is AC. And now let us also construct the segment CC, which of course we may do by construction rule C1. That's just, you got 2 points, you can make the segment. Now, let us look for congruent triangles. And I tell you what, there is a discussion of this, but I'll just simply stay on the diagram to talk you through this. There are now congruent triangles. And again, this is another one of those that I lead you through on the problem set. So I won't actually write out the proof here, but I thought it would be helpful to talk about it. Do you see congruent triangles? Well, look at triangle AZC and triangle RST. Yes, I said AZC, not ABC. Well, let's see. I know that AZ of one is equal to RS of the other. I know that AC of one is equal to RT of the other. Oh, and look, the included angles are equal as well. The angle at A and one is equal to the angle at R and the other. So yeah, those triangles are congruent by SAS congruent. So I said look for congruent triangles, and here they are. So I know that triangle, I tell you what, I'll call the first CAZ, and then let us be careful about how we must name the second. Ooh, that would have to be TRS, wouldn't it? To go from C to A to Z, I went along the single hash and then ended up at the double hash. So if I go T to R to S, I will have done the same in the second triangle. Okay, so those two triangles must be congruent to one another. And then of course it will follow by CPCTE that all their other side and angle pairs that correspond are equal to one another. So here's another pair of angles that would have to be equal. It would have to follow that angle ZCA, be really careful here, it would have to follow that angle ZCA is equal to angle STR. Okay? That is, angle ZCA would have to be another one of those double hash angles because that's what STR is. Okay, so that would follow by CPCTE. Oh, but notice this. Notice that BCA is also a double hash angle, right? So here's what we've concluded. We've concluded that the angle ZCA, which is only a part of angle BCA, is equal to it. But that, of course, is impossible, right? Because as we proved back at the end of chapter 3, the part is always less than the whole, so ZCA, as a matter of fact, is actually less than BCA. Okay, so what was the original assumption that landed us in this contradiction? The original assumption that landed us in this contradiction was that AB was not equal to RS. So what follows that is that AB must equal RS. And if AB is equal to RS, then I tell you what, we'll pop back to a previous diagram here, the initial setup. If it follows now that AB is equal to RS, then it follows that triangle ABC is congruent to triangle RST by SAS congruence. Okay, so we'll have a pair of equal sides, we'll have a second pair of equal sides, we'll have included angles equal. The fact that angle C is equal to angle T is not used at this point in time, and we will be able to say that the triangles are congruent by SAS congruence. Okay, so let's do a little bit of application of this, and then we'll call it quits for the day. So let us prove, and I will do this to you sometimes on problem assignments and on tests. I will simply write out the statement that I wish to prove, and then you have to do all the work after that. So prove that if a segment that bisects an angle of a triangle is perpendicular to the opposite side, then that triangle is isosceles. Okay, so we're going to have to do everything here. So we'll have to draw the triangle. We'll have to say what the given is. Excuse me. We'll have to say what it is that we need to prove. Well, let's see. A segment that bisects an angle is perpendicular to the opposite side. Okay, so here's a segment that bisects an angle and is perpendicular to the opposite side. Okay, so that's what the description says in picture 4. Okay, and this is why we practice so much in chapter 1, this transition from verbal description to diagram that corresponds to it, because you have to do this in proofs very often. And what we wish to prove is that the triangle is isosceles. Okay, and I would bet you in this case that the pair of equal sides will be that AB is equal to AC. Okay, so what is the given? Well, remember that givens are specific, right? We did this when we discussed proof setup back in chapter 3. You have to draw the diagram and then make the given, and what you're supposed to prove refers specifically back to it. So we've got triangle ABC. So we know that BD bisects angle ABC. And we also know that BD is perpendicular to AC. Okay, so that's everything in the given, right? So here's the given segment that bisects an angle perpendicular to opposite side. Okay, so we've got it. And then let's see, how are we actually going to prove this? Well, what we really need to prove is that AB is equal to AC. Ooh, I tell you what, I'm going to be a little bit more careful here. We're actually going to say precisely what we're told to say for our conclusion. That is, the triangle ABC is isosceles. Now, no doubt what I said just a moment ago will be true. We will prove that AB is equal to BC, but then we will need another step to say that it's isosceles, which of course will just be the definition of isosceles. Okay, so that's what we will prove. Well, how are we going to do this? Well, what we really need to prove, as I said, is that AB is equal to BC. How do we get there? Well, in general, if we wish to prove that a pair of segments are equal, we prove that triangles are congruent and then apply CPCTE. Okay, so what are the congruent triangles? ABD and CBD. And they are congruent by, ultimately, ASA. We have two pairs of equal angles. Okay, and we have included equal sides, which is BD is equal to BD. So the triangles are congruent by SAS congruence, ASA congruence, and then it follows that AB is equal to BC by CPCTE. And then at that point, we can just simply use definition of isosceles to conclude that we have an isosceles triangle. Okay, so here we go. So statement from by. So initially, of course, we have the given. And then let's see, we need to know that the measure of angle ABD is equal to the measure of angle CBD. And that follows from the given, where we're told that we have a bisector by the definition of bisects. Okay, and we need the included equal sides equal, and that's really a side in common. So BD is equal to BD, and that follows also from the given, because the given tells us that BD exists, by reflexivity. Oh, and we're going to need to get that angle ADC is equal to angle CDB. And it's going to actually be just a little bit of work to get this done. So let's make sure that you understand how this works. So angles ADB and CDB are right. And how do we know that both of those are right? We know that by the perpendicular lines theorem. Okay, the perpendicular lines theorem says that when we have perpendiculars, we have right angles all the way around. So there are the right angles right there. So it then follows, of course, that the measure of angle ADB is equal to 90 degrees, and it follows that the measure of angle CDB is also equal to 90 degrees, and that follows from 4 by the definition of right angle, of course. And then since both of those angles are equal to 90 degrees, they're equal to one another. So it follows that the measure of angle ADB is equal to the measure of angle CDB. And that's transitivity. Things equal to the same thing are equal to one another. So that's transitivity of equality, of course. And then it follows that once we've got that second pair of equal angles, that triangle ABD is congruent to triangle CBD. And that's ASA congruence. That's why this is here. I wanted an example of ASA congruence. Well, where are equal angles? Well, one pair of equal angles is on line number 2. The second pair is on line number 6. And then the included equal sides are on line number 3. So there it is, SAS congruence. And then it follows that AB, this is a bit of a complex proof, isn't it? That AB is equal to BC. That's, of course, CPCTE. Those are corresponding parts of congruent triangles. So CPCTE. And then we now have a triangle ABC with a pair of equal sides. And it follows at this point that the triangle has to be, sorry, you'll get to write this out. I can't actually do this without and not pull up a menu at the same time. So it follows on line number 9 that triangle ABC is isosceles by the definition of isosceles. Okay, and that comes from line number 8. So I'll let you actually do that. So there's something else that I need to talk with you for just a moment. Okay, and I want to take a few minutes to do this, and we'll definitely come back and talk about this again. Okay, so we have right now SAS, SSS, and ASA's triangle congruence. Okay, we know that those are true one-up postulate two theorems. We can use them in proofs. Later on, we'll prove angle side. And by later on, I mean the next chapter, because we need some other theorems in place before we can actually prove angle side, one about the sum of the angles of a triangle. But I wish to talk about two other possible, maybe candidate triangle congruence principles, and to point out that they actually don't work. That is, they actually have counterexamples. The first of these is ASS congruence. Okay. Well, you know what? Let me go back. You know what ASS would have to say, right? It would have to say something like this. Well, let us say that we have two triangles, right? And I'll just draw a quick picture to illustrate this. Let's say that we have a pair of equal angles, and then a pair of equal sides, and then a second pair of equal sides. And notice that the equal angles are not in between the equal sides. So this is not SAS, okay? So let's be really clear about that. That's not SAS. ASS, if it worked, would say that these triangles have to be congruent. However, ASS does not work, okay? There are counterexamples. So let me show you a counterexample to this. So here's a particular semi-complex kind of diagram. Think about it like this. I start with a isosceles triangle ABC, and then I extended the base out to point D and then connected that up to the vertex of triangle ABC. Okay, so look at this. I have then in this triangle two triangles. Well, I have actually three total triangles, but consider these two triangles ADB and CDB. Okay, ADB and CDB. Well, angle D is a part of both. Okay, so here's what I know. Okay, I know that angle D in one is equal to angle D in the other. Okay, ooh, I also know that AB is part of both. That's really kind of cool, isn't it? Not only do they share an angle in common, they share a side in common as well. Oh, and then as I work my way around the triangles, I know, ooh, excuse me, I got that wrong. That's DB is equal to DB. So that's DB is equal to DB. So let me get this right. No doubt you were deeply confused by this. So again, as we work our way around the triangles, the angle at D in one is the same as the angle at D in the other, and then both have side DB. And then finally, as we work our way around the two triangles, we find that for one, we have AB, and for the second, we have BC. So look, we do have the ASS pattern, right? We do have a pair of equal angles, an angle in common, and then a pair of equal sides, a side in common, and then genuinely a pair of equal sides. However, the triangles are not congruent, okay? That is, though they fit that ASS pattern, the triangles are not congruent to one another. So what this is, it's a counterexample to ASS. So you can't use it, okay? That's the point that I've just made, okay? Pay close attention here. Don't just sort of let this go by quickly and just think that, well, Dr. Mason said that, ASS, and so I'll use ASS in my proofs. Absolutely not. If at any point in this course I ever see ASS used in an attempt to prove that triangles are congruent, that is automatically wrong. Automatically, ASS does not work, okay? Now, here's another one, AAA. AAA would say that if two triangles have equal angles, they must be congruent. Well, we will have a whole lot to say about this later on, but I think I can probably convince you right now that it doesn't prove congruence, because look at my diagram. Would you agree that something like this is possible? A little triangle and a big triangle with all the angles equal to one another? Well, like I said, we will have to consider this in more detail, but you probably find it quite plausible that something like this is possible. But are the triangles congruent? No, absolutely not congruent, okay? So let me make this really big and bold. They are absolutely not congruent. So what is this? This is a counterexample to AAA. So if at any proof, any time in this class from now until May or June, whenever we finish up, if I find a line in a proof that says that these two triangles are congruent by AAA congruence, I know that that is wrong. Your proof will be defective. Okay, so here's where we stand as regards congruence. Here's the congruence scorecard, I call it. Does SAS work? Yep. it's a postulate. Does SSS work? Yep, it's a theorem. Does ASA work? Yep, it's a theorem. AAS, well, officially we're agnostic about that at this moment in time. We will prove it in chapter 4, but we haven't proven it yet, so don't use it. How about ASS? Nope, doesn't work. It has counterexamples. How about AAA? Nope, doesn't work. It has counterexamples. So that's where we stand as regards congruence.